logistics. If you have not joined any of our GoToWebinar sessions before, on the right side of your screen you should see a panel. And in this panel you're going to be able to see, to ask questions. You can type as a chat on the question, should be a little question mark. There's also a button to raise your hand, so it's in the little shape of a hand. People that have their hands raised at the end of the presentation, I will unmute the microphone so you can ask questions or make any comments that you might have. During the presentation, all the attendees' microphones are muted. You can use the chat box to send questions in. And Leonard will make breaks during the presentation, and I'll read the questions for him, and he'll answer as many as he can. Any questions that are not answered during the presentation we'll answer by email later. Also, as just a last suggestion here, if you do have problems with the slides not refreshing often enough as Leonard is going through the presentation, you should see a little button that looks like a square. It's called View in Full Screen Mode, and that will force the slide to refresh. So if you push that button, it will force the slide to refresh. Okay, with that, I'll pass the word now to Leonard.
Thank you, Christine. Good afternoon, everybody. It's a pleasure to be here presenting this webinar. We are having a very good response on our webinars, and I believe that it has been something very useful, and we are also getting very interesting feedbacks. So today's webinar, we will talk about customer experience. This is a buzzword that is becoming very popular, and the reason for it is that people are becoming frustrated, you know, by measurements and statistics that they are using. And I have been approached many times in the trade shows and so on, and people ask, what is happening with my network? My KPIs are great, but my customers are not satisfied, and so on. So it's very important then to understand what does affect really the customer experience, and why measurements and KPIs do not really represent it correctly, and what is the solution. Okay. Just for the ones that didn't attend before, I would like to introduce myself. Leonard Korovaichuk, CEO and CTO of CelPlan International. Have been in the telecom field for more than 45 years. Started with vacuum tubes, if you know what it is. And I have 13 patents. And we published here in the company 2 books. One book is Designing CDMA 2000 System. Although it refers to CDMA 2000 system, it's really half of the book is about designing wireless networks. So it has a lot of very important information about maps, projections, databases, propagation models, and so on. So it's a good reference book. And then we have the LTE, WiMAX, and WLAN network book that was published in 2011. It goes until release 8 of LTE. And now we are doing our 2nd edition that goes until release 12. It should be published in the end of this year, most probably beginning of next year. It's more than 1,000 pages. We are also writing other books under contract with Wiley, network video that speaks about public safety and so on, backhaul network design that covers very important issue that is the backhaul of the wireless networks, multi-technology networks that speaks about everything between GSM and LTE working simultaneously, and smart grid network design. That is something that will be probably ready by 2016. Some of those books we already have the covers done by Wiley. A little bit, very briefly, about our company, CelPlan International. We are a very unique company. We are employee-owned. So our engineers, our technicians, they own the company. And we have a very large international presence. We are headquartered in the USA, more than 500 employees today, and we are already 20 years in the business. We have subsidiaries in six countries, but we operate worldwide. We are totally vendor independent, and we are autonomous. We don't have investors, nothing of this sort. So we are really an independent company, very solid. And what we do is network design software. We have a whole suite of software tools. We do network design services, network optimization services, and network and performance evaluations. We provide services to equipment vendors, operators, and so on. And we do a lot of high-level consulting. So when people have a very difficult problem, they generally come for us and ask our help. We do RFP preparation, business plans, audit. We interface with vendors, we negotiate for operators and so on. And we do a lot of specialized things like aeronautics, smart grids, windmill, and so on. We do perform network managed services, multi-technology. We support all technologies, backhaul, small cells, indoor, and so on. That's enough about us, so let's go to this webinar series. This is a series that we conceived because we felt that there was a need in the industry. There was a lot of misinformation going around, and you know, we are the ones that have to give the bad news to the customer, saying, well, yeah, you were promised a lot of things, but or you're doing things not the way it should be done. This is the reality, that's what you will obtain, and so on and so on. So the first webinar, we give it in May 7th. It was about dimensioning traffic in user networks. Today we will give a very, very brief explanation of what we did in this, explained in this webinar, and all of this is available on our website, YouTube. You can look at our presentations there. So if you missed it or you want to recapitulate, you can still look at it. Then on July 4th, we said, okay, the traffic is characterized. Now we need to consider overhead and dimension the LTE network. And this is a large issue. So it was a very large presentation, a very long presentation. It's also available, and we will do today a very brief overview of this presentation. And then we will talk about today's topic, that is how to take into account customer experience when designing a wireless network. So this is today. The next seminar will be about LTE measurements. Then it will be optimization of LTE parameters, spectrum analysis, and MIMO. So it's a whole series of webinars that goes until November, and I hope you enjoy it. Just some words about webinar 1 for the ones that didn't see it, or just to recapitulate some things, because we will use all of those issues, all of those concepts in today's webinar. I proposed in webinar 2 a challenge about webinar 1. We had 200 participants from 44 countries. So I think this was a very record for us, at least. And the challenge was I gave the abbreviations of the countries, and if people would be able to identify all the countries. So here's the answer to the quiz. On this webinar, basically, we try to dimension user traffic. In LTE, traffic is data, and the way to characterize it is totally different from voice, mainly because there are several levels of quality that have to be assigned to data traffic. So the first thing that we need to do is to characterize the services and the quality offered to those services. So we have to identify quality requirements and so on. So here we have several services, and we have the quality index, defined by 3GPP, and each one of those services will have guaranteed data rate, maximum data rate, or it will not have just a guaranteed data rate. It will have a accumulated data rate. And also it will have a retention priority and so on and so on. One thing that is very, very important and is to associate each service the average size of the packet, because this will impact the capacity of the LTE. You will see that LTE has many, many bottlenecks, some very serious, and one of the things that will play a role will be the number of packets to be transmitted. One thing that we defined was the difference between tonnage and speed. And basically what we said is that for each service we need to define the amount of traffic, not the speed that the data is being delivered, but how much traffic we are delivering. Unfortunately, both are expressed in the same unit, data rate, kilobits per second, but when we speak of capacity, we need to speak about tonnage, that is the amount of traffic that has to be delivered over a large period of time. And one thing that we found, or actually everybody finds, is that services, the amount of traffic depends on the type of UE that is being used. So for different UEs, we use different amount of tonnages, and that has to be dimensioned. So in this table here, we are dimensioning the unitary tonnage per service. And this varies region by region. So this has to be adjusted in every region because there are cultural and other variations that are peculiar to each region. Besides this, the 3GPP has a QoS class identifier that stands for QCI, and this QoS class identifier, the 3GPP establishes 9 classes. The operator can add additional classes to those classes. The classes are with guaranteed bit rate and non-guaranteed bit rate, and we will explain this a little bit later, why we have those 2 classes and so on and so on. The problem starts then when we are dimensioning traffic is to calculate what is the unitary daily tonnage per terminal. So let's take a smartphone. A smartphone will have email, and that's the estimation of the email. We'll have web access, music streaming, and so on. So here we did the estimation for the different services for the downlink and the uplink for smartphone, tablet, USB, and modem. So once we have the unitary tonnages, and those tonnages are related to the monthly plans that the user will sign in. Then we are able to dimension the network traffic. So basically what we say is the number of terminals of UEs for each type of terminal equipment, and based on this we can then do the calculations, what is the total traffic of the network. And this is the peak traffic. But we will see later that we will take this peak traffic, distribute it geographically, and also distribute it in terms of time. So it's very important, but this is the peak traffic of each terminal. That's why we have here the daily busy hour factor. Although the busy hour factor for some terminals can be different, even smartphones, you can have smartphones in residential area and in business area, and so on and so on. So how to consider overhead in LTE dimensioning and what is the impact was the second webinar. And we were very pleased because the number of participants and countries increased. We went to 250 participants and 49 countries. So we were very, very pleased, and it's really amazing the power of internet. You'll be able to communicate with 49 countries, 250 people in one single presentation. It's beautiful. So basically in this webinar what we said is that, look, we have to calculate the capacity of our system, so see how much overhead we have and so on. To do this, first thing we need to do what we said in webinar 1, we need to tell what is the service demand calculation. So how much traffic is being demanded by our users. In the webinar 2, we will calculate what is the availability to transmit data in our network. So how many cells we have and how much each cell can carry. But to calculate this, we need to understand all the overheads. And LTE does have a lot of overheads that reduce significantly the capacity. We also have to understand how the data is mapped. And for 3GPP, the mapping information is called control information. So how does this control information tells where the data is being sent and under which conditions, which modulation scheme and which transmission scheme and so on and so on. So we have to calculate the control capacity and the data capacity. And once this is done, then we can calculate the number of users per cell in our network. So everything is interconnected, and that's why we need to do a very precise step-by-step approach. But it's very, very essential. You will see later that for the customer that we understand the traffic distribution and we apply the traffic correctly on the network. In webinar 2, before we could even discuss this in more detail, we said, well, we need to do a refresher on LTE because there are many, many concepts that have to be understood, and we focus not on everything but on topics related to capacity and overhead. So we explained the downlink frame in reasonable degree of details. Basically, one of the issues that we called attention is what we call that a frame is a 10 millisecond. It has 10 subframes, and each subframe has 1 millisecond, okay, 1/10. Now, this 1 millisecond is called a TTI, transmission time interval. And this interval is very, very important because any transmission has to start and finish inside the TTI. So packets are built to be sent within a TTI. You may send more than one or many packets, but if a packet is being sent, it starts in the TTI and it should finish in the TTI. Otherwise, it has to be divided in more than one packet. There is one area in the subframe where the mapping information resides, and it's the beginning of the frame. It can have 1, 2, 3, or even 4 symbols. And this area basically 3GPP calls control area, but where the mapping of the data area that follows is done. This mapping information has to be blindly decoded by the UE. Another thing that is very, very important is that this mapping area maps not only the transmit data from the downlink, but also the transmit data from the UE in the uplink. So the mapping is all done here, and all these decisions about what to transmit when is done by the ENB and is informed in the downlink frame. Then we spoke about the uplink frame, and basically is very similar, 10 milliseconds, 10 subframes, and each subframe is a TTI also. So the only thing here is that there is no mapping. The mapping is done in the downlink. So the downlink tells you UE where it should send the information in the uplink. And there are some control channels on the side, mainly for ACK/NACK and random access. And there is one area that is an area for UE random access. Differently from Wi-Fi, that the whole channel is used for random access, in LTE, only a small portion of the uplink frame is used for random access, and not every frame obligatorily. So this is something that has to be dimensioned according to the number of users and the number of accesses. We spoke a lot about protocol layers, how the information is organized, what happens when a packet enters the network, and what kind of overheads it gets, what kind of error correction it gets, how it is multiplex segmented, where the FAC forward error correction code is applied, which kind of modulation, how antennas are mapped, and the same thing then for the uplink and so on. Then we spoke about channels and signals. Yellow we depicted the downlink, and in blue the uplink. And here we went to a certain level of details. And unfortunately, the only way to really understand LTE is to be able to understand all those acronyms. But you will see that they are very logical, and it's not as difficult as it looks to remember them. We also introduced the concept of transmission mode. The transmission, in an LTE network, the UE can use many different transmission modes. And the transmission mode is something that is negotiated between the UE and the ENB when the UE joins the ENB. So are we using a single antenna port, transmit diversity, open loop spatial multiplexing, closed loop spatial multiplexing? Are we using multi-user MIMO, and so on and so on? And things are beamforming. So things are getting more and more complex as the transmission mode increase, and some transmission modes were only introduced now in release 12. So basically, this is an evolution, and it's very, very important to define the transmission mode which the UE will use, because this also will define many formats, many constraints, and many bottlenecks that we will find going forward. So the transmission mode is very, very important. Then we spoke about modulation encoding schemes. LTE has a much more sophisticated modulation encoding scheme compared to other technology. Although it uses only 3 modulations, QPSK, 16 QAM, and 64 QAM. It has many possibilities of coding rates associated to those modulations, and this is because LTE uses turbo coding, and the turbo coding allows us to do perforation and also allows us to do repetition. So part of those codes are really based on repetition. You can see that some codes here, the native code is 0.33. So it's 1 data to 2 error correction. This is what comes from the code. So all of this here implies that the correction code beside this 1:2 ratio has repetition, and the lowest code has a repetition of close to 10. So this is very, very important to understand and to analyze the code efficiency and so on. The LTE has 29 code rates based on modulation MCS schemes, and it will choose one of those. Although the measurements in the LTE are limited, channel quality indicators, CQI, they are limited to 15 codes. We also spoke about frame organization. We have here a downlink frame besides the uplink frame. Remember that the uplink frame is really built at the receive antenna on the ENB, and both have the transmit time interval very well defined and so on. Then we spoke about channel equalization and how it is done. Basically, you have to equalize because the broadband channel is so wide, you will have frequency variations and time variations. So you have to equalize, and to do this, we use reference signals, or you can call them pilots, that are known signals that are sent, but they become an overhead. And now, mainly when you have multiple antennas, you have to have one reference signal for each antenna, and that increases even more the overall overhead and so on. So here we illustrate using our new product called CelSpectrum. We illustrate one frame. This is the RF channel response. Here we see the response channel, RF channel response in 3D. Here we have the RF, and here we have time. So we can analyze how you can see clearly the fadings and so on. And here we have the actual signal. So you can see here very clearly the control channel part and so on, and you can see the fadings happening here. Next, we spoke about the downlink control area. Remember, is in each TTI is the area where the mapping resides. There are some also AC and NAX symbols there, but basically it's the area when the mapping resides. And this is here depicted in orange, and we went to some degree of detail on this because this is one of the bottlenecks. Because of a tentative reuse of one in LTE, the control channel has a lot of redundancy, and every single bit that you add, it is multiplied by a large factor, so 10, 20, 30. So it really becomes a bottleneck, and we explained this. We spoke about the PDCCH. We also spoke about the uplink random access area. That plays a very, very important role because that's how the UE synchronizes to the system, and also that's how the UE requests bandwidth to send information. And the request is without information. It just says, I need bandwidth. And it's up to the ENB to figure out how much bandwidth the UE needs. Okay. Here we explain the data allocation. You saw the allocation of the control of the mapping, and now here we explain how data is allocated in the fee, and you can see that it's quite a complex process that has also bottlenecks. The issue is so serious that in release 12 the control channel was extended, and now we have an enhanced PDCCH that is using part of the data channel, data area in the TTI, because there was a lot of bottlenecks, and it was decided to use part of the traffic channel. But sometimes the traffic is the bottleneck. So there are a lot of analysis that has to be done. You cannot just, play by ear. You need to understand your traffic characteristics and so on. Then we went to talk about cellular reuse, because there is no way that you can really have a full reuse of one everywhere. Maybe in some areas of your cell you can have a reuse of one, but as a general rule, you are a cellular network, and you have to have a spacing in between the same resource. usage. And this spacing is because resource usage will require a certain SINR. So what we need to do here is that we need to analyze what is this reuse. And we did this very extensively. And here I'm showing only the summaries of the screens of webinar 2. But here basically we say for different RF patch slopes, and for different values of SNIR, what is the typical reuse that we can use. And you can see that in some cases when you have really very bad slopes and so on, you have to use very large reuses. Then we spoke a little bit about reusing LTE and what are the thoughts that the 3GPP and the industry has about it. Basically what the 3GPP says is a very general statement where they say, look, this is my ENB, I have 3 cells, and I can divide my cell in 2 areas, an external area and an internal region. Okay, so, and of course in the external area I definitely cannot have reuse of 1, but in the internal area I may have a reuse close to 1. It doesn't tell you how to do it, and it leaves this to the vendors to decide. And it says that if there is a lot of conflict, you can always use lower modulation coding rates with repetition and so on, trying to overcome the issue of interference. But of course, using lower coding rates will decrease your capacity. So what is best? It has to be analyzed case-by-case basis. But we still believe that a good and solid reuse pattern will provide you the best outcome. It doesn't mean that there will not be areas in the cell where you can have a better reuse than you will have in the whole cell. So, and we will discuss this more in today's terminal. Basically, for broadcast information, 3GPP solution was use low coding rates because you will have 100% of interference. So you will have probably to work with negative SNIRs. 3GPP also considered the advent of intercell interference coordination that is already on the 3rd patch and still doesn't provide a solution. We have ICIC, we have enhanced ICIC. Now in release 12 we have further enhanced ICIC. And none of them really solves the issue completely. If you go to the literature, there are 4, I said here 4, there are 4 and some variations. So the first variation is no ICIC, use regular whatever reuse patterns, and that's it. Then start-stop index has been proposed. What it means is, well, this cell will start from subcarrier 1 up to subcarrier 20. The next cell will start from 20 to 40 and so on and so on. So it will give you the start-stop index for allocation resources. It's equivalent to using a reuse pattern. But the start-stop index can work in frequency but can also work in time or a mixed combination of both. Then some universities proposed, well, let's do only a start index, let it grow, and if there is some kind of conflict because there is not a stop, so you will invade the other cell area, well, then we resolve the issue by repetition, by lower coding rates, and so on and so on. Other people propose random start indexes. Well, let's start anywhere and see what happens. Again, we will use repetition and so on. So there is a lot of theory, a lot of ideas in the field, and each vendor is doing its own solution, and it's very important to get from the vendor what is the solution they are using so it can be properly modeled and understand, because this solution will affect many other parameters in the network. Well, LTE specifications, I baptize this as bit scrubbing. Because of this issue of reuse of one, mainly in the control area, what happens is that every single bit that you add to the control information, it will be multiplied by 10, 20, 30. So 3GPP created a lot of variant in the specification just to cut 1, 2, 3 bits. So it does blind decoding, it does implicit addressing, and this created multiple options, and so it makes the specification very complex. Of course, for the user it doesn't matter, but it matters for the UE because it requires a lot of processing. And I was very curious why my phone would become hot when it was in my pocket. And that's the reason, because it has to do a lot of processing to avoid those, to have an economy of few bits that if added, will solve all those issues. So we have high data spreading rates to be able to use reuse of one in the control area at least. In the traffic area for sure it is not used, because otherwise you will have no throughput at all. And also there are very complex transmission modes being figured out, which efficiency is also questionable. So be very careful of claims. Many of those claims, they only apply in laboratory and not in real life. Well, 3GPP provided some mechanism to avoid resource conflict. They didn't say how to solve the issue, but they say, well, you have some interfaces that you can use, you have some messages that you can exchange, and this will help the vendors to devise methods that will allow them to minimize interference between cells. We ourselves have applied 2 applications, and I will speak this in today's topic. So here I'm still refreshing the webinar 2, and that we do some kind of regionalization, we create subcells, and so on. So we try to address this issue also. The next 2 slides, they were in the webinar 2 presentation, but there were so many questions about them that we decided to redo the slides, make them more clear how they were derived, and for you to understand what we want to transmit and inform. Basically, I will start here with the definition. We start with a frequency of 1 gigahertz, a bandwidth of 10 megahertz, a transmit antenna gain of 12 dB, receive antenna gain of 0 dB, and a noise figure of 10 dB. Then we use an Okumura-Hata slope of 35 dBs. Why Okumura-Hata? Because we don't have a database here, so we use a standard model. And then we calculated what is the SANR for IWGN, for a Gaussian channel and a relay channel. A Gaussian channel is the one that you have line of sight, prevalent line of sight, and in the relay channel you don't have any prevalent line of sight, it's all non-line of sight. So based on this, basically, if we plot here distance in kilometers, and here the transmit power, and here is the base station, the transmitter. So when we start, we are very, very close. We start with low power, and we can increase the power. We are transmitting at 64 QAM, and then we are changing the slopes. And 64 QAM goes until here, and at this moment we can change to 16 QAM. In this example, we only used these MCS, modulation and encoding schemes. We didn't use all the 29 because the graph will become very messy. So we choose some spaced, and it shows basically what is the criteria you jump. But you can see that there is no much power variation after a while, because what you will do, you will change the modulation scheme. And so the power variation is only in the beginning. But this graph here on the top is done for line of sight. Well, we have another graph here done for non-line of sight. And you can see that the coverage is much, much smaller. And this is a big issue when you are designing a network, because you need to provide coverage indoor that is non-line of sight, but at the same time you have people transmitting outdoor, and you have a lot of interference. This can be better exemplified in these next two graphs, when we have here the modulation radius for the different schemes. And you can see that the high efficiency schemes cover a very, very, very small area. This area is the radius is not much smaller, but the area is much smaller here than it is here. So you really need to position your cell accordingly in relation to your traffic distribution, so you can maximize the capacity. Another very, very, very important conclusion is that larger the cell, lesser is the traffic capacity of the cell. So if you limit your cell to 16 QAM, the cell will have much more capacity than if you limit it to QPSK with a repetition of 10 or even of 5, whatever. So the capacity really depends where you limit your cell. And also you will have cells that are very, very small, because they are non-line of sight cells. And you need to design the network for both. So this was still in webinar 2. This curve here is something that we developed. Basically it shows, forget the bars for a moment, the bars are related to this side. It gives the bits per symbol for each modulation. Let's look at the curves themselves. So if we have a 1 gigabyte monthly plan, and we say, well, we will limit our coverage to 16 QAM, we can put 20 users per cell in average. But if you say, well, now my users are using 4 gigabytes per month, and I'm limiting, I can only have 5 users per cell in average, and so on. So this gives a good idea of the different capabilities of the system. At this point at the webinar 2, we said, well, now we did the refresher. We are ready to start dimensioning and planning. So what are the overheads in LTE? And then we explain with the control and data overheads, PDCP, RLC, MAC headers. Well, I will not read all the acronyms here, but there are a lot of control and data overheads, downlink frame overheads like reference signals, ACNACs, and so on, uplink frame overheads, and then we need to understand also the cell load, the reuse factor, handover margins that we need to leave, and also the statistical distribution in relation to the average. So all of this has to be considered. Well, what are the possible bottlenecks? Where can we expect the bottlenecks? Well, PDCCH is a channel that maps the location of the data, and this is one of the large bottlenecks, mainly when you go to smaller packet size like VoIP. This is the channel that will limit the PDCCH and the PUCCH. Then you have the PDSCH, or the data channel, that also can be limited mainly when you have very large packets. You also have to dimension properly the random access area, because this can be a big bottleneck. We already spoke about the PUCCH and the PUSCH. Then the question is, what do we need to dimension? In LTE, there are many parameters that have to be dimensioned. The number of downlink control symbols, the PHICH scaling factor for ACNAC. So depending on the number of packets, you need more or less area for ACNACs. The PRAH iteration capacity, the PUCC iteration capacity, and many others. I will not go here in details. You can listen to the webinar number 2. It's in our website and YouTube. What should be planned? Well, look at how many parameters you need to plan in LTE. There is a whole webinar that I think is 2 webinars from now where we discuss this in great details. Well, all of this is very complex, so we designed a traffic calculator that basically uses the traffic dimensioning that we did in webinar 1, and then we calculate the capacity of the cell with several parameters. This calculator was done for internal use. After the webinar, we have been inundated by requests for this calculator. Unfortunately, it is not really ready to be delivered to the public in general, so we are discussing now internally to put some more effort and be able to release this calculator in our website probably 2-3 months from now. But this calculator will then give you what is the end capacity of your cell based on the different constraints that you choose here. And then we will go to today's topic, but before this we have a break for questions.
Yes. First question, the traffic calculations, are they deterministic or statistical?
Just one moment. Okay, the traffic calculations, they are of course statistical. You will work with an average, and then you will have some kind of deviation and so on. But they are statistical because, of course, you have different users have different statistics. Fortunately, here we still need to work with averages. I don't like to work with averages, but because you have so many users, the average has some validity here because you have thousands of users and so on, but it is a statistical parameter.
Okay, second question, when we have a mixed environment, indoor and outdoor, for example, which one should we use in the design?
Both. And that's very essential. You need to consider indoor users, outdoor users, and you can see that if the cells, they have very different sizes, so one, you have to provide continuous coverage, while the other you have to provide interference. So you really need to work with both, with outdoor and indoor, and consider both coverages when you do your traffic and interference analysis.
And one last question, how does the UE choose which MCS it should use?
Well, in LTE, the UE doesn't choose anything. It's all chosen by the ENB. The UE even doesn't say how much data it wants to send. It just, what the UE does, it measures the received signal, it informs the received signal to the ENB, and it tells the ENB that it has data to send. The ENB analyzes the measurements from the UE, but those measurements, you will see in the next webinar, they are not highly reliable. They are very, very questionable. So it's basically a gross ballpark figure where to start, because then the ENB will adjust the MCS according to the a number of errors of the HRQ retransmissions that it has to do. So based on this, it will adjust, fine adjust the MCS, and it will tell when it, and then it will check, well, how much data the UE has to send. And the only way to find this out is through the buffer status report that the UE sends when it sends a MAC message uplink. If there is no previous messages, the ENB just guesses and gives an initial value, allocates the area for the uplink transmission by the UE, and it tells the UE where it should be placed and which modulation code the UE should use. So the UE doesn't really have much say in defining how much data it can send in each TTI, neither which MCS to use. It's all ENB decisions. Any more questions?
No more questions.
Thank you. Okay, so let's go for today's topic. So this is webinar number 3, and we will discuss how to consider customer experience when designing wireless networks. Customer experience is a buzzword that is, everywhere you go, oh, let's do customer experience. But what is customer experience? So the content of this webinar is how to evaluate customer experience, what factors affect customer experience, parameters that affect customer experience, SINR availability and how to calculate it. And you will see why SINR appears here. And then we present our conclusions and a brief presentation of our new products. So the first point is how to evaluate customer experience. Well, let's suppose that we have an existing network that is there operational. Why not we ask the customer, what is your experience? Well, in principle, the customer expects the same performance as it has from wired networks. Second, that not all customers have the same expectations. So if you ask one customer or another one and another one, each one will give you a different answer. And another issue is that customer focuses on symptoms, not causes. So it will say, well, it's too slow. The issue is not too slow. It doesn't have capacity. So to understand also the customer feedback, it's very, very difficult many times because it basically is not a technical person, so it doesn't have any knowledge about the network. It just will show content or discontent. So we need to take into account the customer experience through other means to figure out, how to deliver it. Well, a lot of companies said, well, let's look at the network statistics. Well, first, the statistics are humongous. Second, it's a lot of work. And third, those statistics represent the network as a whole, and they don't really identify specific areas. So some vendors went to extremes to identify, small areas, some small packets, and so on. But the network statistics, we will see later, have another issue. They are average values, and they generally consider good against bad, and they give you the average. But you don't want to design your network for the average. You need to design the network for 95, 97, 98% of the time, so it becomes a little bit more convoluted, more difficult to use those network statistics. And the network statistics don't tell you really what is the issue. So a lot of people then resort to performance tests. Well, performance tests generally cover a very small part of the network at the same time, and measuring a network in different places at different times is close to useless. Okay, if you don't have something that will take this data and allow you to compare it, You know, you are measuring things at different hours, at different times, in different places. So people resorted to, well, let's use the UE information then. UE is doing measurements. Let's use those measurements as verification. The problem that the UE measurements are very, very unreliable, and we will see this next seminar why. So again, it's using a very unreliable method to define how reliable is your network 98% of the time. So there is something missing that will put everything together. And what is missing is a capability of predicting the performance. So if you are able to predict the performance, then you can make sense of the KPIs and you can make sense of the measurements and you can put everything together. It's like having a table with 3 legs. If you remove one of the legs, the table will fall. So basically that's very, very important, is to be able to predict your performance. But to predict your performance, you will see you need to model correctly your network. And that's a lot of work initially. But once it's done, you can then calibrate using network statistics, you can calibrate using performance tests. What happens if you have a new network or expansion of improvement? You don't have statistics, you don't have measurements. Even if an expansion or an improvement, and we see over and over, you know, people do a change hoping that it will improve. It doesn't improve in one area, it ruins another area. And then, you know, it's a big issue, and you keep correcting the network and so on. So again, it's essential to predict the performance and to properly design your network. If you are building a bridge or a building, first thing you do is that you calculate, you know, how strong should be your bridge and your building. You don't, you know, well, let's build it and then we put some reinforcements later. And that's what people are doing with wireless networks. Well, let's deploy it, collocate with GSM and see what happens, and then we fix it. You will not fix it. There is no KPI analysis or measurements that will fix a badly designed network. So it's better to invest a little bit more money in the beginning and properly design the network. And then we can compare the predicted performance with the actual results, and we can calibrate the prediction model. And that's another thing that the people need to understand, that the prediction model is based on statistical assumptions and so on, so it can be adjusted with the field experience. So that's why I speak always of this 3-leg table. Other issues, KPIs are not standardized and are implemented by vendors. Vendors are, I don't know why, but they are very reluctant to document the way they measure the KPIs. Even 3GPP, you know, they document the measurements, and every single people I speak about some measurements have a different understanding of the 3GPP specifications. And that's why I speak of RSRP, RSRI, and RSRQ. So each test vendor says, well, that's 3GPP specification. It doesn't work very well. That's I did my own version here, all those measurements and so on. And then when you compare, you know, you see, well, this vendor understood this understood that. So it's very difficult really to figure out sometimes what is being measured exactly. Besides this, vendors do not like to present bad statistics, mainly when they design the network. And this is a big mistake that people do. They ask the vendor to design the network in an RFP. Well, the vendor that uses less sites, less cells, will probably win the RFP or get the best possible price per cell. So it's not fair with the vendors to ask them to do this, because they will never be able to design a proper, more expensive network. Okay, so they will have to design by the minimum, and sometimes even not enough. Another thing is that KPIs provide average results. Good performance masks bad performance. But clients, they don't give any credits for good performance. KPIs do. And that's one of the reasons that KPIs fail to represent, the reality. And LTE measurements are also highly deficient and have a large potential of giving misleading results. And again, there is generally not enough documentation to know exactly what is being measured. So, but if you put all of this together with the performance predictions, then you can figure out, well, that's probably a deviation of these measurements, this is probably a deviation of the KPI, or this is a deviation of the prediction that I have to adjust. And all those three are giving similar results, or then you can say, now I have a calibrated model. You will spend much less capex, much less effort, and the customer will be much more pleased, much better customer experience. So my conclusion is that customer experience prediction is an essential step in the design and operation of a wireless network. No measurements or statistical KPIs analysis can fix a badly designed network. And here I illustrate what generally happens when you try just to use one of these methods to fix your network. You have a badly designed network that is or insufficient in terms of cells or overloaded. You will be chasing your tail and spending money, throwing money away, basically. So trying to fix a network after deployment or change is expensive and result in unsatisfied customers. One thing that is very, very important is that customers like to have the same experience. So they can even accept that one area has the bad coverage. But what they will not accept is that one area has a good coverage today, a bad coverage tomorrow, then a good coverage again. They want consistency. Okay, of course they would like to have all good areas, but they will accept some bad areas. But when you start changing those areas, then it really gets very frustrating to the customers, because they only will remember the bad experiences. I think, no, I have another one and then we have another break. Okay, what factors affect customer experience? Well, first, IP network performance is different from switched networks. Why? Well, I again would like to stress the difference between data speed and data tonnage. Speed and tonnage is expressed in data rate in kilobits per second. So I will try to give you an example here. I have a 10 megahertz LTE channel, 2 transmit antennas, 3 control symbols, the mapping symbols, and this results in 5,500 resource elements per TTI. Well, I cannot use in one single cell all those resource elements. So I will use here a factor of 7, a reuse, and this gives me 800 resource elements per TTI. What we do then, what is the maximum speed? So I can say, well, in this TTI, I will send only this packet from this user. Well, this user will get an equivalent data rate of 800 kilobits per second for this packet. If it is using KPSK, if it is using 64 QAM, it will be 1.6 megabits per second. Now, okay, he sent the packet, he has nothing else to send. Later on, he will have to send another packet, but now he is sharing with 40 users the frame. So he has to wait now 40 TTIs at least to send his packet. So the average that he will get over time is not 800 kilobits, but it's 20 kilobits per second. So this is speed and this is tonnage. So that's the difference between speed and tonnage. Speed is the instantaneous that you get to send one packet. Tonnage is what you get over a long period of time. And you can see this 20 kilobits per second will probably represent 1 gigabyte a month plan. Okay, 20 kilobits per second in the busy hour. Okay, so now let's see what factors affect customer experience. First thing that we need to understand is that IP communications we divide in two groups, interactive and independent. In the interactive group, a typical example is a web browsing. So we are doing browsing in the web, and we have a web page being downloaded in our screen. Well, a second web page will not be downloaded until we make a choice. So that's what we mean by interactive. So, and this choice will be slower the network is. So there is not really much, basically the tonnage will be adapted to the capacity of the network. But we have some IP communications that are independent, so there is no action required from the other side. This is the case of voice, video, and voice streaming, live video, and so on and so on. The first case, basically, you cannot have errors. So you are sending an Excel spreadsheet or a web page. You don't get holes in the web page because you are using a protocol that has error correction like TCP/IP. In the second case, you are using a protocol like UDP that doesn't have error correction. So you will have clicks in the voice and you will have flickers in the video. So it's very important to understand that there is an iteration and that the traffic adjusts itself. So, but how do the customer express the network experience? Well, they will say the network is slow. The speed of the network is slow, but in reality they are referring to tonnage. Very seldom the issue is speed, really, because what happens is that because of the bandwidth is very large, the speed is high, but the tonnage may be low because you are sharing with too many people. Another issue is lost sessions, bad quality, mainly for independent IP communications, and what I said before, customers like consistent performance. If I have, several areas that are good and one area that is bad, well, they will probably accept it. But now if I have good area and tomorrow it is bad and this is bad, tomorrow is good, and so on, they will only remember the bad parts. So I think whoever is designing, whoever is feeding with the network, try to avoid too many changes because you improve here, ruin there. Try to understand what the issue is. Do a proper design. Okay? Well, let's speak about parameters that affect customer experience. The most important parameter, in my opinion, is the network design. There is nothing you can do to fix a network design, no KPI analysis, no measurement, if the network is not designed properly. You will not, if you have a network that is already overloaded, doesn't matter the measurements, there is nothing you can do. So you need to understand the network design, and that's very, very important. So if you want to collocate your design with the existing towers, 2G and 3G, you can do it, but analyze the outcome before you spend the money. Maybe it's better to have a smaller footprint and have the right coverage. Okay. Then network settings. LTE has hundreds of parameters to have to be properly dimensioned. You cannot just use the 4 values. Simple things like cyclic prefix. In one cell it can be normal, in the other it can be extended. And this has to be measured and analyzed and defined. Then resource planning. This is probably the most complicated thing in LTE because 3GPP left it to open. So you depend on the vendors, how the vendor algorithms work, and those are generally proprietary solutions that they don't like to disclose so much. But you know, we need to be firm and get this information, and vendors need to be cooperative in this. And then try to do a plan that avoid interference, because the vendors will also in the end benefit if you have a way of reusing resources, avoiding interference, and so on. You can use third-party vendors that provide, you know, solutions for ICIC and so on. But many of those solutions are very questionable also. So don't just believe in marketing information. Another issue is overload. In LTE and basically 4G technology, what happens is that when you deploy a network, it will work because you have very little traffic, very few users, and the possibilities of the conflict are relatively small. Even in time, they don't speak, they don't send data at the same time, and you can correct with you know, lower codes. But when the traffic starts raising, the performance of the network will drop very, 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 very slowly until it reaches a point when it drops like a waterfall. So overload is a big, big issue in this kind of networks. And it's really a very thin, you know, barrier between the graceful degradation and the waterfall. So you need really to design and properly model your traffic requirements. Interference. Well, LTE has inherited issues with self-interference between itself, mainly in the control channel. So vendors have to provide a solution, or you have to consider this in your design. Another thing that we find very frequently is bad internet connection. So it doesn't help, you know, to have the best wireless network if your backhaul cannot support your traffic. And finally, signal to interference noise ratio. This is a very, very important parameter used to optimize the network, but it cannot and should not be calculated in average, because an average here is totally useless. You need to design your network not for 50% of the time, you have to design it for 95, 98% of the time. So how do you calculate SNIR statistically? And we will talk about this very, very, very soon. So let's go and analyze capacity and traffic calculation. So before you can even analyze anything, you need to model your network. To model your network, you need to do capacity and traffic allocation. And we already explained this in webinar 1. So here is the screen where you calculate, you know, your traffic, your distribution. So, okay, you have now the total traffic per type of UE for your whole network. The question is, how is this traffic distributed in your network? Well, part of it will be outdoor, part of it will be indoor and ground floor and at different floors. Okay, so it's very important to model and distribute this traffic correctly, because if you don't model this, there is no prediction that can work. So I always say to people, modeling your network is about 75 to 80% of the effort. And then everything else will work. But if you don't model the network, you know, trash in, trash out in a planning process. Another thing is that you also have to distribute your traffic in time. You cannot just consider 1 hour of the day. So what happens is that, see here we have residential traffic. Look first just the downlink. And here we have business traffic. You can see that the business traffic grows when residential traffic drops. Well, generally what we do when we calculate the traffic here, we calculate for the peak hour. So what we will use now, we have to model several hours of the day. And in each hour of the day, we will use different proportions of this traffic. Okay? And only then we will be able to analyze the network as a whole. In some hours of the day, you don't just get the peak traffic. The traffic is smaller than peak, but you have to model this because maybe this traffic is located in different places. Here we have traffic distribution for outdoor and indoor in residential layers. So this is an outdoor pedestrian. Here are outdoor in vehicle, and only happens where? In streets. Indoor ground, indoor 4th floor, 10th floor, and 20th floor. And although there are very few pixels with 20th floor, they probably are interfering more than the indoor ground. So this is very, very important. And this is residential. Look at the business. So now business layers are much more dense, but they only happen in certain hours of the day. So modeling this is very, very important. And then using a capacity calculator to estimate the capacity of the average cell. At this moment, we have a chicken and egg issue because, yes, we have the traffic, but how much traffic will each cell carry and how much interference it will have? Well, we cannot calculate because we didn't allocate the resources yet. And what are the resources here? Resources, we will see later, are what I call resource block groups or subframes or basically resource block groups. So those resource block groups will have to be allocated, but at this moment, but to allocate the resource block groups, I need to know how much traffic will be carried by this cell. So the way we broke this egg and chicken is that we create a noise rise. A noise rise is an estimate of how much interference we will get in this cell. And that's enough to start the process. So then we will be able to assign traffic to cells and do the network statistics in terms of serve session, reject session, serve traffic, reject traffic, and queue traffic. So once this is done, then we can start planning, and we plan a lot of things. Link budget, channel frequency, cyclic prefix, PCI, cell and base station identity, tracking areas. Just in relation to the PRAC, look how many parameters we have to plan. The uplink resources, neighborhoods for different technologies, interrupt, handover, resources, and so on. But all of this depends on one thing. Resource planning depends on the correct evaluation of the SNIR between cells. Once we allocate the resources, now we can consider the interference. And this is done through multiple iterations. And in our case, we do what we call a dynamic interference. So we model our network dynamically. And now we get also the output statistics here in terms of served session, reject session, and so on and so on. But what are the conditions so we can calculate SNR availability?
Len, can you do a little break here? You skipped the last
Yes.
one. I have a few questions. Okay.
Yes.
First one is, could you elaborate a little bit about the statement, the main mistake done today is to simply collocate sites with 2G, 3G network without analyzing the outcome?
Well, many of our customers, because of the availability of existing infrastructure, existing leases and so on, they deploy the network just by collocating sites with 2G and 3G sites, deploying LTE in the same sites. And the argument that we hear is the following: well, we deploy and then we fix it. And the way they plan to fix it is to look at the KPIs, to look at the measurements, see where there are issues, and try to fix the issues in those locations. But there is nothing really you can do if your network is already badly designed. So many cases those collocations don't make sense. It's like, you know, again, doing a building. Well, I don't know which floor the building should support. I will copy the building on my side here that was done by the neighbor, and then I will hope that it works. If it doesn't work, I will go and reinforce it. Well, maybe you over-designed it. Maybe the reinforcement will be very expensive, and definitely the tenants will not be very pleased. Same thing with the wireless network, you know. So, okay, you can collocate, but before you decide to do it, do the analysis, do performance predictions. And I don't blame people because performance predictions generally didn't work. So a lot of people lost credit. They don't believe in performance predictions. And the reason we will see next is that first, the traffic was not modeled correctly, was not distributed correctly, the equipment was not modeled correctly, the prediction tools, models were very deficient, and the SNR calculations was completely wrong. So all of this then contributed that the performance predictions were very deficient. Today we have already tools and ways of doing much more elaborate performance prediction as long as the input data is correct. So it's always very important. Even for analysis of KPI and measurements, to model properly your network. This is about 75 to 80% of the effort. I hope I answered this.
Okay, one more question. What is the difference between traffic throughput and traffic capacity?
Well, again, it's I use both, but I see people using it differently. There are people that says that the throughput is data speed, and others say that throughput is tonnage. So throughput is a name that can be used for both. I prefer to use data speed and data tonnage, although I must confess many times I speak about data throughput. So the correct thing would be to separate the two concepts. Speed is data speed, tonnage is data tonnage. So data tonnage is the data rate over a long period of time. Data speed is the data rate over one packet. Okay, and that's what we need to understand, that are the distinction. Throughput, I see in the literature being used for both.
Okay, thank you. That's all I had now.
Okay, thank you. Okay, going back to SNIR and how to calculate. Well, first, to calculate SNR availability is a statistical term, and that's not easy to do. So let's see what is required here. Well, first thing, we need to have an appropriate propagation model. What happens is that we have been using propagation models that were developed in 1954, 57, like Okumura-Hata, or others that were developed 20, 30 years ago. So wireless, the propagation didn't change, but the constraints of the propagation model changed a lot. Now we need to consider building, we need to consider outdoor and indoor. So what does a propagation model have to have? Well, it must be capable of doing outdoor and indoor simultaneous predictions, because the majority of the users today are indoor. It must be capable of considering fractional morphologies, because in a path you don't have a single morphology. You have 10, 20 different morphologies between the transmitter and the receiver. It must be capable of doing 3D propagation analysis. RF doesn't know gravity. It will go over the building and around the building. to the left, to the right, and so on. So you cannot only do the propagation on a vertical plane, you need to do it also on the horizontal plane. And also it has to be capable of predicting path loss at different heights. So you cannot just predict at ground level and then say, well, I have 3 dBs every 10 meters. Doesn't work. You have to clear the obstacles. There are other diffraction factors and so on. So you need to have an up-to-date propagation model. You need to have a representative traffic distribution. Distribute the traffic outdoor and indoor at multiple heights and different hours of the day. If you don't do this, sorry, trash in, trash out. And then you need to have a valid signal level representation, a statistically valid one. You have to consider independent fading variations. This is a big mistake that people do. Oh, the signal is fading, remove 5 dB from each side. Sorry, it's not what happens in the field. One side can fade, the other not. So try to simulate this at the same time. And also consider all possible interference sources with their statistical distribution. And that's what we will discuss very soon. Well, in terms of prediction model, we use the K3D prediction model. Basically here we can see the depiction of this prediction. You can see very clearly the antenna patterns, and you see what happens when the signal penetrates inside a building. So this is a building here. And you can see when the signal penetrates and when it leaves on the other side. Okay, you can see that on the top of the building you have a stronger signal than you have on the bottom and on the back of this of the building, and so on and so on. So this model we developed because we found a lot of issues with other prediction models. So this was many years, and this is a new model. It is published in our last book, the LTE by Max. So it's a published model, and we are getting fantastic results with it. Then the next step is to do the traffic simulation that we already explained with noise rise, do the resource optimization. But in resource optimization, we need to consider the SIR analysis, and that's where I would like to spend some time to explain what is the issue. Let's suppose we have here a cell, and we are sending a signal to a guy that is being interfered in the downlink, and we have another cell that is using the same resources and is sending the signal to another user, but now it is being interfering here. Well, first thing, the signal doesn't have a signal level. It has a distribution because of fading and so on. So a signal is not static. The interference, let's analyze the interference. Well, the interference comes from this cell. This is a view from the top to this point. Now, the strength of this interference depends which user is being served. And at each moment you have a different user being served. So this is proportional to the amount of traffic that you have here. So what we do, we analyze for this cell what is the average and the distribution based on every single pixel of the served area and its traffic load. After this is analyzed, then we do it for many cells. So now we have here the interference. You can see that is much wider, and we have the signal. Well, we know at the same time that we need for our design goal is a certain SNIR, what will define what is our worst modulation scheme that we want to design. Remember, looser the modulation scheme, less capacity the cell has. So it's an engineering design decision to say, well, I want to use 64 QAM 0.33 or 16 QAM 0.33. Well, I need so many dBs of SNIR. But if you slide here, you will see that you can be here and the SNIR is being reached here, or you can be here and the SNIR will be reached here somewhere. So now we have a statistical possibility of getting this SNIR, and that's what we call an availability. So we need to assure that, and you can specify what availability you want, but the advantage of the availability is that you can add availabilities. You cannot add SNIRs, it's meaningless, but you can add availability of SNIR in a statistical way. So what we do is exactly this. We calculate for every single pair transmit-receive, what's a single possible combination of transmitters, what is the availability of the signal at every single pixel in the served area. And this is a little bit different for the uplink, because now the interference comes from the user to the uplink. And each user will have a different path loss. Well, this looks very, very complicated, but fortunately the tool does all of this for you, so you don't need to worry about it. You just specify what is the SNIR target that you want, and it will give you the availability for every single pair. And here is a demonstration. Basically, you have the signal, and you have a lot of interferers. And those interferers are represented here for one single pixel traffic bin. You have here the best server, and you have other possible servers. So the traffic of this bin has to be distributed between the best server and the other servers. And then you have a lot of interferers and a lot of noises. It's very, very common to have 20, 30 servers interferers in one pixel. So all of those pairs have to be mapped in what we call the interference matrix. And the only way to map this properly is using availability, because you can add availability statistically. So after we do this, then we can go back and do the resource optimization, because now we are modeling the SNIR correctly. And because we are using the availability, we can really optimize the networks, all the parameters that we need to be optimized. Just to speak a little bit about interference and reuse. Well, we already spoke about reuse in the second webinar, and I already addressed this here in the revision. There are several concerns about reuse. In LTE, there was a goal of having a reuse of 1. They figured out, of course, that this is impossible. You can have a reuse of 1, but then you have to use very low coding rates, and that's eats the capacity the same way the reuse eats, or even worse, because the coding rate does not really eliminate interference. It basically eliminates fading. Well, I think we are running out of time here, but basically, yes, you can improve the reuse factor that typically is a reuse factor of 7. In LTE, because you have some tricks of using central areas and the internal and external regions of a cell, maybe you can vary this reuse between 3, that you can achieve in very special circumstances, and 9 that is applicable to difficult situations. In average, it will be a little bit below 7, 5 point something, and so on. But yes, there is some improvement over traditional planning methodologies. And the way to do this is, in our opinion, to use resource block groups and then divide those resource block groups between the different cells. This we already explained also. Reuse in LTE I explained also. I would like to talk a little bit about our patent applications. Basically, We have 2 patents. They will become public probably in 30 days from now. They were filed about 5 months ago. And here we have the traditional methods of reuse. Some of them is discussed in the literature and so on and so on. What we did is that we say, okay, we should not consider a cell as a single entity. We should break the cell in regions, and in our case we break the cell in up to 9 regions, and those regions are defined by the amount of neighborhood measured by the cell. So if a cell cannot measure any neighbors, it can basically reuse 100%, reuse of 1. But it is measuring a lot of neighbors. That's this number of neighbors will basically define the reuse of the cell. So that's where the patterns that we applied, and there are other things like dynamic allocation of regions. So we give one region to one cell, another to another, and then we give a region between the 2 cells that they can use their own regions as they wish, but when they go to a shared region, they have to communicate that they will use part of the shared region to the other cell. So it's a simpler method of doing IC-IC. So conclusions, and then we have a break for questions. In our opinion, proper network design is essential to achieve a desired customer experience. It doesn't matter what you do, you need to do a proper design, the same way you design a bridge, the same way you design a building. Fixing it later doesn't work. There is no amount of field measurement, network statistical data analysis, SON or IC-IC procedures that can fix a badly designed network. Then the network was not designed properly. There is nothing you can do without redesigning the network. You need to have advanced tools with statistical analysis capabilities to do a proper design. So not any tool can do this service. Field measurement, network statistical data analysis are important auxiliary tools to calibrate and adjust design tools. And also SON and IC capability should be considered in the optimization process. Many of those capabilities are available in the market today, but they have to be taken with a grain of salt because there is a lot of over-promises. So, Christine, is there any questions before we go to new products?
Yes, I know you're short on time, so a couple of questions here. If you're not currently using a similar network to, the one you're trying to design, where do you obtain data to calculate the tonnage if you don't have any statistic information yet?
Well, very good question. Yes. Remember that I said that the customer expects to have the same performance as their wired network. So one way of getting this information is to monitor your wired networks. In the beginning, when we started all this process of data analysis and so on, I installed in the company here in my desk and other people and in the company as a whole, I installed sniffers. And we analyzed, what was the usage of each protocol. And that gave us the first idea of how much traffic the wireless network would have to support. This was many years ago, so at that time there was not yet the expectation that the wireless network would deliver the same quality of service as the wired network. But today is what the customers expect. So we were in the right path. And so if you don't have a wireless network, try to analyzing your wired network, and it will give you a good idea of what applications are being used and so on. You may have to do some adjustment because in wireless, maybe other applications will be more important than in wireline, but there are a lot of similarities.
One more. Your SINR study sounds like an SINR study for point-to-multipoint systems. How does the tool determine the number of UEs required for this SINR study?
Well, we do the SNIR not based in the number of UEs, but on the traffic distribution. Basically, what we do is that we define the traffic that will be coped by each cell, and this traffic is basically defined by well, okay, no, sorry, I have to correct my statement here. Yes, we distribute the users geographically, and because we have the average already, the average traffic per user, so it's very, very important to be able to distribute the users geographically for different hours of the day. And for this, we use all sorts of information. It can be car traffic, it can be business size of businesses. We use, I forgot the name now of the company that provides us, suppose for Chicago, we modeled 500,000 business with the number of employees in each business to be able to generate the business traffic. Housings, so we use different statistics from different organisms, and in few cases, in places that third world countries that those statistics are not available, we generally sit with engineers and we draw regions and we make estimates and distribute the DUEs according to different hours of the day.
Okay, do you have time for one more, Leonard?
Yes, yes.
Okay. What would be the better or most used propagation and traffic distribution models for 4G technologies such as LTE?
Well, we use the K3D model today, but that's not really 100% true. It depends on the quality of your database. Poorer the database, less stringent should be your propagation model. So what we do, because not always we get the database that we want to get, and also not all LTE designs are the same. So in some cases we have, very light areas, we don't have a lot of buildings and so on, so we can use any propagation model. So what we do is that we take the database and we calibrate all our propagation models. We have 6 different propagation models, each one with at least 64 sets of parameters. But we calibrate with the best the database, and we look which propagation model gives us the best results. For dense areas, building areas, K3D has consistently giving the best results. For areas where the database is not very good, Okumura-Hata is giving the best results because it's a very average, very uncompromised propagation model. Not the regular Okumura-Hata, but the one that we implemented with fractional morphologies. So this one is, and we have others, but generally I would say that we stay between those two. Sometimes we use the K2D model also, but it depends on the quality of the database and so on. And what was the other part of the question?
The other was the same, but about traffic model simulation.
Well, we implemented our own traffic simulation. We call it a dynamic traffic simulation, and that's very important because basically everybody does a kind of Monte Carlo simulation, and the Monte Carlo simulation, you can do it statically. But what happens is that you do snapshots and you adjust the snapshots and so on and so on. But there are, when you finish the snapshot, you have queues, you have accumulated things, so you lose the dynamicity. And in a real life, things are moving constantly. So What we found a method of providing this dynamicity to the Monte Carlo simulation, and that's what we call a dynamic traffic simulation, where we consider, what is the size, we simulate the size of the queues, the size, so we have an overflow from one snapshot to the next, and that helps us to give much more efficient traffic analysis.
That's it.
Okay, sorry, I'm thirsty. Okay. Just to finalize, let's speak briefly about our CelPlan new products, CelSpectrum and CelDesigner. I promise not to take much of your time because I'm running out of time. CelSpectrum, very interesting product. I love this product. We just came out with it. Basically what it does, it's a spectrum scanner. And of course, you are familiar with spectrum scanners for LTE, but all those scanners, they only do one-dimension measurements. CelSpectrum does 2 and 3 dimensions. So typical example of one dimension is power level, RSSI, RSRP, RSRQ, and so on. Now 2D, here I have 2D, very unique multipath. So here we have power and here we have time. So we measure all of these for every single pixel. And then we have 3D measurements like received signal level per resource element. So this is an LTE frame, and we store this per drive test pixel. And then you can see this in 3D. Here the RF channel response, also in 3D. So it's a very, very powerful tool that does unique insight into the RF performance. One thing that it does also is being able to analyze the signal received from 2 transmitters. When you have MIMO, you have 2 transmitters. It does a correlation between those transmitters over a drive test. So it will say which percentage of the drive test you can use MIMO, which percentage MIMO will not work. And then we can do an interpolation and create a prediction that can then predict over the area what percentage can be using MIMO and where percentage cannot be using MIMO. The other product is CelDesigner. It's a new generation of planning tools, very, very advanced, and is a collaborative work with several operators that we have been doing during the last years. So CelDesign is a new generation of planning and optimization tools. And here I explain the reasons, of course. Wireless networks are becoming extremely complex. The new antennas, it's really something very, very amazing what is happening. Is a revolution with the dynamic antennas, the power amplifiers per antenna element, multi-tilts in the same antenna and things like this. So CelDesigner supports simultaneous multi-technologies, full network representation from site, tower, antenna housing, and so on, and implements the K3D models, and it does everything that I said that a tool has to do. It does automatic resource planning, automatic cell planning, and does also performance predictions that are very, very important. It has full integration with Google Earth. We don't export to Google Earth. We bring Google Earth into our tool. That's very unique also. It does a network master plan that is very unique. It simplifies SON and ISIC. It integrates field data and KPIs. And does backhaul planning. Just to inform, we have a boot camp basically in, well, this is not for EMEA region, and this is on July 22nd and 23rd and 29 and 30. The first module is a 2 days wireless communication fundamentals, so it's independent of technology, and the second module is 4G technologies and in-depth analysis. And the next webinar will be August 6th. These registrations are open, We have a limited number, and I believe that this time we even exceeded the number that we had of openings. So register soon, and you can see in our site what is the content of this webinar. And that's it for me. Thank you so much for your attention. I'm very glad with the number of attendees, and this presentation will be available for download from our website probably on Monday. Chris?
Okay, thank you everybody.